start with the presentations of the block number 4 of the workshop. We are going to hear the talk of Francesco Niosi from the MORELab laboratory Politecnico di Torino. The talk is Renewable Resources Modeling with MOST software.
Hello, I will have a brief introduction about myself. I work at More Energy Lab and I'm currently starting my third year of PhD. I work on mooring system characterization for both floating and wave energy converters. And also I managed to deal with topics such as validation, hydrodynamic farms and standards. MOST, which is acronym for Matlab for Offshore Floating Wind Turbine Simulation Tool. It's a comprehensive platform in which you can model both aerodynamic, hydrodynamic, and mooring loads. So you can include in one software all the peculiarities of such systems. The different blocks are managed, are solved by different tools. For example, the hydrodynamics is modeled, the frequency domain hydrodynamics is solved from open source tools such as NEMO, coupled with Wec Sim and Salome Mecha. And Simulink allows you to solve multi-body systems, dynamics, quicker than other kind of potential flow numerical models. Aerodynamic can be computed using panel methods or lookup tables to speed up the simulation. And basically this is a, let's say, overview of all the loads that the software can account for. The question is why we needed to develop such a model, because there are different commercial software which are actually able to do the same. The answer is we needed that because we wanted a software that was able to be inserted inside the optimization processes. So basically it needed to be fast in all its components. And is it more suitable than other software because it can be parallelized in clusters in Linux platforms or Windows. For example, you can see the difference between Orcaflex, which is a commercial software, against the MOST. So basically, you can simulate 1 hour of time domain simulation in 10 seconds with MOST, while you require minutes with Orcaflex, depending on the time step you choose. We had to use MOST because when we start with a project, we start from the concept, so the idea, and at the moment that we have the idea or the solution that we want to test, we need to understand how to model the devices and how to optimize the device. Once we made the optimization inside the optimization tools, the numerical model, to use it, has to have the right trade-off between accuracy and computational cost. So you cannot use very heavy and high reliable tools. Once the optimization phase is finished, then we went to the design phase in which we can improve the reliability of the software, but also we can change the way of make numerical modeling. For example, using CFD codes, which accounts also for viscous effects, but they require high computational cost. For each design, for each project that we have in mind, we need first to understand where it can be located, such that we can understand how to run the optimization. For example, if we want to optimize a wave energy converter for a predefined site of installation, which can be in Mediterranean Sea or ocean or another sea, and any kind of installation site, we need to understand on which parameters, environmental parameters, run the optimizations. So basically, we define the operative states for which we want, for example, to maximize the energy productivity, and the extreme states. So to understand the extreme events, the highest loads that the system will be subject to. So that's the pre-processing of the data. And here, I will briefly make some examples of optimization path that we made using MOST. In this case, we wanted to optimize the material, so the cost of the substructure for a floating offshore wind. So basically, here you can see just the idea that was behind the optimization. We used MOST to simulate all the dynamic simulation, and then we were getting back the results. So for example, the pitch amplitude of the turbine, which should be minimized to maximize power. And in this way, we could have tried, let's say, hundreds of thousands of solutions within a couple of days of simulation. Another application, for example, was the optimization of a mooring system for the floating offshore wind turbine, in which we can, again, the issue is the computational time again, because we needed to understand and simulate for each individual inside the optimization algorithm all the scatter, all the waves, thus we arrived to, let's say, an optimum results, which actually was chosen on the Pareto front of the optimization for other kind of decision at the end. We picked only one individual on the Pareto front, and that's the results of the optimization. So it was a taut leg mooring system with all the characteristics displayed here. Another application that we used for MOST, it was the modeling of a complex system in which the offshore platform is connected with wave energy converters. So basically, you can manage the hydrodynamics of the platform and the wave energy converter using a sub-block of MOST. And you can couple the dynamics of the platform and the WECs inside all the simulation tool using, in this case, for the hydrodynamics, Wec Sim. This is another kind of application. So basically, it's again a wave energy converter coupled with a floating platform. The easy thing, the good thing of the software is that you can easily shift different wave energy converter, place them in the right position according to your needs. And it's otherwise starting from zero to model a new solution of an hybrid platform would be super time consuming for all the group. This is again another application in which the turbine was integrated with the OWC device. And again, we decoupled the problem. We added the block of the oscillating water column to the main block of the simulation, and we could manage to understand the whole dynamics of each component of the system. Of course, it's we did good, all the optimization and the results were nice and fine, but we needed to be sure that MOST actually works, and we didn't make any mistake during the code writing or any other mistake that can arise. So we performed some validation processes. This is a validation against a floating offshore wind turbine without any WEC. So it's just simple hydrodynamics with the substructure of the 15 megawatt wind turbine designed by the NRL. And the experiment was carried out in Plymouth University. So basically they released all the data set and they told us, okay, let's run a validation with different university to see how we can get the results. So basically in MORELab we used 3 different software. Orcaflex, I was talking about it before, which is the commercial software. MOST and StarCCM, which actually is SCFD, so it accounts for viscous effect. In MOST and Orcaflex, we of course introduced the linearized damping coefficients such that the model was well tuned for this substructure. And we managed to obtain good results for all the degrees of freedom, plus also the line mooring tensions. Another experimental campaign, which is the correspondence experimental campaign for the OWC device modeling, was carried out in Rome. So basically, in the 3 columns, which are here, here, and here, there are the 3 OWC, and the main structure is the spar. Validation of this experimental campaign still need to be done, but we had some previews about the results, which looks good. The last experiment that we made for validation was carried out in Delft, and accounted for, again, a floating offshore wind turbine, but this time we applied a wind thrust, the wind force, applied with a wind winch. So basically we were applying constant tension at the nacelle, and the motor torque was controlled in voltage and current. The scale of the experiment was pretty small, so we could understand also the differences between full-scale modeling and small-scale modeling. The validation will be published soon. Yes, so basically these are more details of the experiment, which is actually the same mooring system that I showed in the optimization processes. And finally, I thought about, okay, we optimized, as I was saying before, the whole system for Mediterranean Sea. And then I thought, okay, but what happens if for any reason, for industrial reason, or the system had to be replaced? I didn't know to come in Argentina, but I decided that, okay, let's get a rough sea. And I decided to make some tests for Tierra del Fuego. So basically, I downloaded all the data, all the environmental data of the last 20 years from basically a grid which is 50 kilometers times 50 of this area here, outside Cape Horn. And I managed to build a wave scatter and environmental contour of this site. And then all the data, by the way, I downloaded all the data from the available website of ERA 5. And I ran the experimental tests for these waves, which is HS of 15 seconds and a peak period of 16 seconds. So basically, the system was subjected to higher loads than its design condition. And actually, he managed to resist. And yes, that's a video of the old acquisition that we made. So basically, here we were controlling the wave maker, and here we were acquiring the motions and the tensions on the mooring system load cells. And all the optimization process was done with MOST.
Thank you very much, Francesco. We have time for questions.
Thank you very much for your presentation. Very nice presentation. I was wondering if the software that you developed, are you planning on extrapolating it to a system of wind turbines, maybe a few of them, and what would be the implications of doing that on the system, on the software? I mean.
So basically, you mean modeling wind farms?
Exactly. Floating offshore wind farms. Exactly.
Actually, that's a current task that we are dealing with. So your question is super fit to the argument. And basically, we are adding different blocks of the same turbines inside the Simulink code. The more tricky thing is the interaction between the WECs of the turbine and the hydrodynamics interaction. Because to, let's say, make some optimization processes, accounting also for the interaction, we need to decouple the single system and use the, for example, simplified interaction codes, which can allow you to not compute the hydrodynamics and aerodynamics for each single turbine.
Thank you very much.
Okay. We have time for more questions. Of course.
Thank you, Francesco. Just out of curiosity, how did you manage to work the moorings in the experiments? And can you, maybe it was just something in the picture, the kind of moorings you used in the design looked like tension moorings, but with chain. Are these vertical anchors, or is it just the drawing? It's a catenary system.
Actually, this is. Oops. This is a nylon prop, and the chain is just at the bottom and near the fail lid because of safety reason. But actually, in the experiment, if you pass from the full-scale model, which is this one, to the small-scale model, the chain wasn't needed because basically what we scaled down was the stiffness of the mooring line. So we used two configurations, one with springs, which mimics the stiffness of the equivalent full-scale mooring line. And in the other case, a nylon line. The tricky part, this is the second configuration, the tricky part is that the stiffness of nylon line is not linear, like the spring. So it was hard to get a good compromise between, let's say, the diameter of the mooring line and its stiffness. So it was...
That's very tricky, yes.
Nice presentation, and looks like a great tool. Just in terms of the static wind winch connection, is that force controlled or position controlled?
No, actually, when I said controlled, it's not controlled. Basically, what we were doing, it was applied at the beginning of each test, a constant force, by tuning the voltage and the current going to the motorbike, to the engine. Which was applying a force that we were reading by the load cell on the motor. And at the beginning of each test, we had a constant force, but then when the structure was moving, it wasn't controlled at all. So basically the force was fluttering, but at super high frequencies and wave frequencies. But the shuttling was very small with respect to the mean value. For validation purposes, we could actually, I'm gonna follow two ways. One is to import in the numerical model the wind thrust profile, let's say the input that acquired, and the other kind, just the constant thrust, to see and understand also the differences and the error that I could obtain related to this problem.
But it mightn't be too difficult just to put force control on the winch. which would then take into account the motion of the platform.
Yes, that's the second step that we want to do. I made this experimental campaign in Delft. So basically, they gave us all the equipment and all the facilities to do that, and they had just this wind winch. But for the next experiments, that was actually what we're gonna do.
I know at a recent visit to Michigan Tech, they have a similar setup with a floating offshore wind platform model in the tank, and they have a robot arm that's moving the top of but it's force controlled. So you put a prescribed additional force onto it. It's actually exactly the same thing as wave makers in a tank, that you're able to just add on what you want rather than be reactive to what's happening outside.
Yes.
Looks great.
Also, your suggestion, is great, and I was thinking about implementing this, but for time reason and other stuff, we couldn't do it.
Sure. Thanks.
Okay, thank you very much, Francesco, for your presentation.